So, when you open the ANSYS software, it will look something blank like this. To get all the tools visible, click on View, Reset Window Layout, and you will get this all the tools back. Now, this is the Fluent which you will be working on in terms of aero modeling. So, double click on that. When you work on any CFD simulations or aerodynamical simulation, these are all the basic chart flow where you need to note it about. You cannot directly work on any simulation. You need to first have an idea like what exactly are you going to work on, what type of simulation it is, and like why each and every tools are important, what to use and what not to use. So this is basically the overall flow chart where you people need to analyze before you're working on. So now in the geometry, right click on it. So you will find like two different type of structure. I mean like designing tools, space claim geometry and design modeler. So both are something like 3D modeling softwares of like ANSYS itself, similar to and like CATIA, SolidWorks or Fusion 360, something like that. Both of it is are the same but different user interface. Next is you can import your own geometry as well. So anyways, we will start on with designing a geometry because first we need to come up with geometry, then we need to work on the meshing, then we have to give the environmental boundary conditions, then the solutions. Now right click on geometry, go to space claim. This is called as space claim. Here it works like a 3D modeling software. Okay, you just click on Z axis over here. It will be like this, right? So click on Z axis over here so that you can visualize the overall tool like this. Now in the XY plane, we will be beginning with 2D analysis, right? So I will choose XY plane. And remember, when you're working on any simulation, make sure that it is in XY plane. Now click on the second option, select new sketch. Then you'll be able to get a sketch plane like this. Here you can do the design. Now we will go with the utmost basic design. I'll go with circle. Make a circle like this. You can give diameter as well. Now see, for example, if I keep a circle like this, I click on dimension, click on circle. Now I'll click on this diameter 30. I'll make it as 100 mm and press enter. Now the circle gets a bit bigger. Next is, you cannot directly perform airflow analysis over this circle. You need to create an environment. Because see, if you just zoom it out, you can see the overall environment is infinite. So that's why we will be applying a finite fluid domain. To do that, I'll just click on rectangle and make a big rectangle like this. Now, next is, once I create a big fluid domain structure like this, you might observe like why didn't I make a small square? Why did I make a very huge like fluid domain? The reason is if a supersonic airflow is flowing upon a circle and if there are shock waves being formed, the shock waves are pretty huge by the way. It extends. And to check out what's the maximum length it can range up to, I make sure fluid domain size is quite bigger. Then only I will be able to track it down. That's why I make sure it is like this. Now next is, I will click on the first option, return to 3D mode. So this is something where I'll have to return from 2D sketch to 3D plane. I'll click on this green color box over here. Now you can see a surface being formed up. That surface is nothing but the environment. Now here zoom in, environment, object, right? Now right click on the circle and delete it. The reason why I am deleting the circle because it is simple. Okay, now I'll just click on Ctrl Z. Now right click on circle and delete it. Now there is a cavity in shape of the circle and the environment is a solid. Let me give an example. If you are in a real-time environment and let's say there's an airflow upon any object, the object is solid and environment is cavity, right? But here it is completely opposite. You follow Navier-Stokes equation in order to make sure you're working on a continuous medium. Navier-Stokes equation states that the whole environment you're working on should be treated as a continuous medium. To make sure it is continuous, I just delete the circle over here so that I can see the phase structure cavity. It is nothing but halo, like a hole with respect to circle design. Now I can give the inlet, outlet and all those conditions. Now directly close it. Just close it. Ansys will automatically save it for you. Now right click on mesh, click on edit. Here, this is the overall meshing workbench. So this is something where you'll be discretizing the domain into multiple elements so that you can work on giving accuracy. It is nothing but basically giving increasing the accuracy. Let's say you're clicking a photo. When you click a photo, so over there the clarity depends on the pixel quality, right? The better the pixel quality, clear the image. So same thing will be applied over here. Now just click on mesh and make sure element size, okay? For me it is 353.56 mm, some random number. For you it will be something else. For each person it keeps on varying because we haven't given a proper size for the environment. Now next is it is in mm. Why am I getting in mm? So if you want to change it, you have options here like meter, centimeter or millimeter. So I'll make sure it is in millimeter. Now I'll just click on generate. Just click on generate mesh and you'll be able to get a proper cells over here. Now this thing is called as meshing. It helps in increasing the overall accuracy. Now just look in the center of the circle. It is not exactly a circle now. It is kind of straight lines over here, right? It's a polygon. How to increase the accuracy? You need to increase the overall mesh size quality. To do that, you just click on element size. Instead of 353, I will just randomly divide it by 2. Okay, now again 353 divided by 2, it will be like bunch of like decimal. So that's why it is kind of gonna be hectic. To make it simple, instead of 353, I will assume it is 300. 300 divided by 2, it is 150. Just round it off to nearest simple digit and then divide by 2. That would be the best way. Now again, 150 divided by 2, it is around 75, right? It is easier to divide by 2 if the number is ending in zeros, right? Now zoom out. You can see the cell size has been decreased, but it is not well aligned. It looks a bit weird, right? To give it aligned, I'll choose face control so that I can select the face. If you choose edge, you can select the edges. Point control to select the point. Now I'll choose face control, select the face. Right click, insert. I'll go for face meshing. Okay? It's a 2D now, face meshing. Now just click on generate again. You can see that it will be aligned. Now here, once it is aligned, again you need to increase the cell size. Instead of 75, I'll just give it as 30 and generate. Now this is actually good. It is very precise, but from 30 I will decrease to 15 now. That's the maximum lowest I will go for. I can actually give for more, but this is honestly enough. Next is you need to name inlet, outlet and all those conditions. So to do that, I'll right click on mesh, So I'll right click on mesh. You can go to naming selections, or see, for example, when you're working on any sort of simulations, there are two types: wind tunnel based and next is far field based. Now, when it comes to wind tunnel based, you'll be giving this as inlet. You'll be selecting this line as inlet. This is outlet, a restore wall, and the circle, right? But if you are working on wind tunnel method, that's the most pathetic method ever we can come across with. Because let's say if there is sudden angle of attack change or anything, it rebounds and comes back to the wall where it will cause a lot of interfaces and unnecessary changes in the flow path. So it is very limited. So that's why I will choose a open field environment so that I can name all the edges. Now just click on control key, edge 1, edge 2, you can see it is highlighted in green color, edge 3 and edge 4. Now right click on it and name it. I'll name it as far field, FARFIELD. Far field means open space environment. No interferences. This is the best method for external airflow dynamics. Now again, I'll choose circle, right click, create name it as circle only, enter. So totally in the name selection you can see here, far field and circle has been given. Now I can actually decrease the cell size a bit more, but this is precise enough. But we'll give one last shot. I'll just give it as 5 and generate. Now let it be as it is. Now right click on mesh, click on update. Now at the bottom right corner, it tells you that the meshing was successful. Now close it, close meshing as well. Now right click on setup, click on edit. So once you do with the meshing, you will have to basically give specifications of your laptop. So I'll give double precision, 4 solver processor and click on start. If you don't know how many processor your laptop has, you just go to task manager. Okay, just click on task manager and you click on performance. You will get to know how much cores your laptop is and how many are you getting used right now. You can select it as per your requirement. Now this is called as setup. The first thing which I want you to do is ignore everything on the top. Whatever you see on the top, ignore it. It doesn't exist. Focus on outline view, task page, mesh, basically the main screen, console. Now, next is pressure base and density base. Basically, for low speed operations, we go for pressure based, and for high speed operation, we go for density based. Okay, so now I'll go for density based basically and go to models, double click on energy equation. So why am I turning on the energy equation? There is a specific reason, because let's say there's an airflow happening over an object. There are a lot of energy imbalance, right? The incoming free stream velocity will be having a kinetic energy. That kinetic energy will decrease when it makes a contact on the body surface, and due to friction, it will decrease. So when the kinetic energy decreases, then internal energy will rise. So this gives rise to nothing but temperature. It keeps on going up, and this will cause more imbalances further on. So to check it up properly, I just press OK on energy equation. And next is viscous model. What type of viscosity of airflow are you working on? Now, I think you know inviscid laminar flow, right? Now, these are all different types of turbulence model with respect to environment what you're going to work on. Now, when it comes to external airflow, we preferably go for K epsilon. Two equations are there, okay? K epsilon, K omega. But both are same. What's the difference? The two equation is turbulent kinetic energy and the second equation is dissipation of turbulent kinetic energy. Now K epsilon is weaker version and K omega is stronger version, basically used for like hypersonic conditions or something like that. Now once I choose K epsilon, press OK. Now these are all the like standard properties of this particular turbulence model. Now press OK and close. Now you need to go to materials. Double click on air, then go to constant and make it ideal gas. The reason why I make sure there is ideal gas flowing over a circle, because I should get to know like what if the sudden temperature and pressure changes. This might alter the velocity effect, right? So to make sure everything is in line, so I make sure if I choose ideal gas, it obeys all the different types of gas laws, right? This will autonomously adapt itself to any respective sudden changes. So click on create and close it. You're just naming the environment, that's it. Now this is the most important part. It is called as boundary conditions. So here, click on far field. There's the airflow coming now, the far field. So name it as pressure far field. Here, it will ask you some couple of questions, basically in terms of values. So for that, I'll make sure I mention the overall environmental pressure. So this is something. So this is something where I'll be mentioning the gauge pressure of the environment what you'll be working on. So now over here, for the sea level condition, I'll give it as 101325 pascals. That means, let's say that you're working on a airflow at supersonic speed where the object is at sea level condition, that is the pressure of it. If you're working on it in terms of space, then the pressure decreases. With respect to altitude, the pressure decreases, right? Now for sea level, this is constant, 1 bar ATM, 101325. Mach number. For Mach number, we'll go for 2, Mach 2. Then apply and close. Then next is go to methods. Make sure turbulent kinetic energy is in second order and dissipation is in second order. The process is very simple, okay? We don't even need to give outlet conditions because already far field has been considered as one single environment. In the methods, I make sure everything is second order so that it is nothing but pressure and velocity based stabilization, right? So it should be done bit quicker in terms of calculation. So we prefer that. Then go to initialization and just click on initialize. It's a 10-step process. It's a 10-step process. Once it is calculated, you will get a warning and all. So don't worry about it. Just go to run calculation, solution steering, supersonic, and number of iterations will be 1000. Just click on calculate. So you can find these graph lines over here. What are these graph lines? These graph lines are nothing but convergence criteria based system where you can figure out overall airflow dynamics with respect to x-axis, y-axis, turbulence dissipating with respect to x-axis, y-axis, energy medium dissipating with respect to x-axis, y-axis. All of it will be given over here. With respect to friction and time, it keeps on dissipating. It reduces. I mean, of course, the flow won't be continuous, right? At some point, it will stop. That is what you are planning to find out here. Now, we have given 1000 step for calculation. Now, here it is not even 1000. It is ended at 268 solution. At 268 solution, I got convergence. Convergence is nothing but it shows least number of error in a simulation. In very simple term, convergence in ANSYS is nothing but which helps in determining pressure, velocity and temperature becomes completely zero at certain point. Now that means our system solution is complete and is right to go. So now I'll just go to graphics, double click on contour, just click just click pressure and static pressure, display. This is the shock wave basically for the circle design what we have come across with. The red color is shock layer. The distance between shock wave and the body is called shock layer. It's very thick, right? The red color. And this whole thing is called as shock wave. And this is the flow separation where the flow doesn't contact on the body surface. Now wherever pressure is high, the temperature will be high as well. I'll click to temperature, display. You can see, right? Now at the stagnation point, you can see temperature is very high. I'll tell you what is stagnation point. You click on velocity and Mach number, display. The blue color extended zone is called stagnation point. Basically, flow is separated, flow is not joining. That's the part where the flow it tends to circulate to create a vortex effect that gives rise to sudden temperature spike. That's why you can see temperature is high over there. So now I will close this. Let's try performing a simple pathline animation. Click on pathline. So click on everything, velocity, 50 iteration step, continuous and pulse. So you can see the overall circle behaving, like how aerodynamical it is. You can see a huge boundary layer being generated, a bow shock, surrounding environment being it is under like misequilibrium. So this way you can figure out presence of vortices or any other thing which you come across with and close. Now we will try performing one more design structure simulation because circle is something pretty easy and quick, right? So we'll try on working on something which is like kind of a bit different than what we do. So close this, open one more Fluent because don't work on existing Fluent. It would mess up your precision. Right click, go to space plane. So now I click on Z axis again. So next we'll go for something else, a different design structure. So for that, I'll click on line. We'll make a simple random rectangle, triangle. Something random, okay? Then choose rectangle. It's not even symmetric. I've done it completely random. Then make a huge fluid domain. Then click on return to 3D sketch. Now click on the design, right click and delete it so that you will get good precision. This is called cavitation method. Now close it, right click on mesh, click on edit. So now I'll click on Z axis, go to mesh, but before that, let's name it, okay? Choose edge control, control key, select all the edges of the design and name it. I'll name it as Tri, enter, TRI, that's it, some random name. Now the whole environment, name it as fluid domain or far field. Go to mesh 48 mm. I'll just keep it as 10 and click on generate. So now I'll just decrease it a bit more. I'll go for 5 mm and click on generate. If you click on update, you'll get mesh translation to fluent or successful. Then you need to close it. Right click on setup, click on edit. It's a pretty quick simulation, right? Go to double precision, follow processor, make it as 4 and start. I'll go to display. You can actually unselect or select whatever you want to view. Let it be as it is. Density based. Go to models, energy equation. You need to turn it on. Viscous model will go for K epsilon. Materials go for air. Ideal gas condition. Create and close. Then go to boundary conditions. Far field, pressure far field. So next is on the type of environment, I'll be going for 50,000 feet above the Earth's surface. Okay, so that will be somewhere around like 100,000 Pascal. Very less. Now Mach number, I'll give it for Mach 3, supersonic only. Now when it comes to angle of attack, have a look. When it comes to angle of attack, x is cos theta, y is sin theta. Drag acts on x-axis, left acts on y-axis. Now theta is angle of attack. Cos of 0 is already given, 1. Sin of 0 is already 0, given. Now let's say if it is cos of 5 degrees angle of attack. Cos of 5 degrees is 0.992. Sin of 5 degrees is 0.087. Okay, apply and close it. That's how you give angle of attack. Then go to methods, make sure everything is in second order and click on initialization and start it. Then go to run calculation, solution steering, keep it as supersonic and calculate. So now you can see the turbulence dissipation is like very intensive. So that means that this is a very vigorous flow. You're working on a low pressure environment at high speed flow where the turbulence dissipation will take a bit longer time and it will react completely different. These are all nothing but vortices being generated which will eventually dissipate with respect to time and friction. So you'll have to wait for. So last time when you worked on a simulation for circle, you got convergence at 268 solution, right? Now it is around 700, 800 now. You're still not getting the convergence. So it's not every time you get convergence very quickly, it will take a bit longer time. But if you get it, then it's a good simulation. If you don't get it, it is still a good simulation. Convergence is nothing but a show off. Like you can prove your point. Like what you have done is accurate with respect to environmental setup. So now we got convergence, right? Is it convergence? No. Till 1000 it has been calculated. So it is not a convergence. We have just reached 100% of calculation. But we will at least figure out. Go to graphics, contour, display. Now this is the angle of attack of 5 degrees and this is the shock wave analysis. With respect to design, it is like not symmetrical, right? Due to unsymmetrical body design, you can see the shock wave is completely different. So here is the flow separation occurring. This is the shock wave. That's why I create a very big fluid domain. Next is I'll click on temperature. Wherever there is flow separation, stagnation point will be intensively very high. Velocity. And now next is in terms of velocity. So over here, you can see the blue extended zone, right? So that is nothing but stagnation point. So that actually occurs when the flow is going up now. The shock wave is being formed up. The flow doesn't reattach. When if it doesn't reattach, at some point there will be a separation gap. That is called stagnation point. There will be intense amount of circulation vortex that will generate high temperature because if sudden energy is dissipated and it is stopped, it gives rise to internal energy. That is nothing but temperature. Now in velocity or pressure, there are like many types. Even in pressure, static pressure, dynamic pressure, total pressure. Same applies for temperature as well. For velocity. So as per your needs, you can find it accordingly. Now close this. Go to simulation and reports at the bottom. If you want to see a ready-made report, right? Double click on simulation report. Double click on report outline. Just click on generate report. Now wait till 100% is complete at the bottom. So so that you can get a ready-made report with all the things explained along with the pictures. So now you got a ready-made report generated by Answers. Just scroll down and you'll be able to see all the report format in terms of meshing quality, the overall material properties, the type of airflow, viscosity, the specific heat dynamics, inlet condition. Literally everything will be given over here. Convergence graph, like pictures. So for pictures, you can take the picture automatically by taking a screenshot. That's not a problem, right? To export it, there's an option. You just click on export, export as PDF, and wherever you want to place the location, you can check it accordingly. So that's how you perform the overall simulation.